So we're recording. So this is a discussion of Unit 4, lesson number 3, on simulation, sampling variability in size, and statistical significance. So the first question, how much do NFL players weigh on average? In a Rams of 50 NFL players, the average weight is 244.4 pounds. So do you think that 244.4 pounds is the true average weight of all NFL players? Explain your answer. Well, I wouldn't say it's a true average weight, mainly because I don't know if only asking 50 players would be enough. For those who don't know, NFL teams have 53 players on an active roster. Then they have a practice squad as well. And there's 32 NFL teams. So it's, close to 2,000. I mean, it's over 1,500 for sure, but close to 2,000 professional football players. So I don't know if only interviewing 50 would be quite as accurate. Because some football players are like offensive linemen, defensive linemen are really heavy. They weigh over 300 pounds. There's some who are lighter, more lean, like a wide receiver might weigh about 190, 200 pounds. Kicker is probably pretty underweight. Quarterback usually might be close to average because you want a quarterback who can withstand some punishment if they get tackled often. But I would say no, because sample size of 50 seems a bit small. But it's probably close. Now, which would be more likely to give an estimate close to the true average of NFL players? A Rams of 50 or Rams of 100? Well, I'd probably say 100. If you have more samples, you'll tend to have less variation. So what that means is that it'll be closer to the true average, the more you sample. Now, of course, you don't want to sample too many because then might as well just average everybody then. So you have to, it's kind of like a fine balance. So sampling variability and sample size. Sampling variability refers to the fact that there's different RAM sample of the same size from the same population produce different estimates. Okay, so variability means change. So different random samples of the same size from the same population produce different estimates. So larger random samples tend to produce estimates that are closer to true population value than smaller random samples. Large samples are more precise. So using kind of a sports analogy, I'm not sure if anyone's seen the movie or read the book Moneyball. Has anyone seen it? Anyone wants to share quickly what it's about? Anyone who's followed baseball or who's watched that movie? It was Brad Pitt. He played the lead character.
Well, it's about the Oakland A's, and they're like notorious for not spending too much money.
Mm-hmm.
So they're like trying to figure out the perfect system to like get the right players for not that much money, right?
Right. Yeah. So they're trying to figure out how can they still put a competitive team, even though they can't come close to spending the kind of money like the New York Yankees, for example, or the Boston Red Sox, who at the time were the better baseball teams. And so they had to come up. They had to use a lot of statistics, right? They wound up using some statistical techniques and methods that, or looking at certain metrics that were largely ignored, and they were able to kind of like find those diamonds in the rough, right? Now, in the game of baseball, that could work pretty well. that kind of process. For football, it might be a little more tricky. Football, they only play 16 games. Baseball play 162 games. So you could see why baseball might be easier to pull off because you have more games you can look at. And in fact, actually, there's a scene in that movie where the owner of the A's is a little bit critical of the methods that they're using. And they kind of tell them, the sample size is too low. We've only played about 30, 40 games. Give it a chance. And actually, I vividly remember that year. I think later that summer, they went winning 20 straight games. I was actually at that game, the 20th straight game in Oakland. It was probably one of the most incredible games I've ever seen. And I vividly remember the home run that was hit. The A's were up 11-0. They blew the 11-0 lead. And then bottom of the ninth, the guy who actually replaced Jason Giambi, who was the big player of the team at the time, Scott Hatteberg, hits a home run. And at the time, I didn't know about the story. And then, a year later, they published a book. And they're like, and I read the book, and my mind was blown. I was like, oh, my God, this is amazing. And ever since then, I've looked at the sport totally differently. Anyway, but when you have a larger sample size, you tend to have more data you can look at. You could probably pull off in football too. You just have to figure out what you're looking at in football. Like maybe looking at the number of plays that happen in a game. Every football team usually plays about 60 plays in a game. But the larger sample size helps. So for baseball, statistics actually makes a big difference. Of course, some people will point to Game 6 of the World Series. They don't know what happened in Game 6 of the World Series. What mistake Tampa made that everyone was so up in arms about. If anyone would follow that game at all. Maybe no one really watched baseball this year, but someone share? No.
No, if the Giants aren't in it, I'm not watching it.
I know. Okay. Yeah. The Tampa Bay Rays, they had this system where they never let the starting pitcher pitch more than they would never let the starting pitcher see the opposing lineup for a third time. So when you have you have a pitcher, they see the batters 1 through 9, then they see him again 1 through 9, and then they would refuse to let the starting pitcher see it for the third time because they think that the third time the batter has a better chance of getting a hit, especially a team like the Dodgers are a really good team. And then they bring in all the guys from the bullpen. Well, that backfired because the starting pitcher for Tampa in Game 6 was actually pitching the game really, really well. And he should not have been pulled. He was really upset. And then, of course, Tampa Bay started giving a bunch of runs. And so some people say, like, well, yeah, in the long run, that was the right decision. But for that particular moment, it was not. But they were using statistical analysis, and they're looking at a large sample size throughout a whole season. That over a whole season, yeah, that was the right decision. But in that moment, which, by the way, Bruce Bochy of the Giants rarely did that kind of stuff. Like, he actually just uses gut instinct. So sometimes gut instinct, and for me who loves math, sometimes you just got to just treat each situation in a unique way. So sometimes you could throw stats out the window and if you just use your gut instinct. Sometimes that's a better way to go about life in general, not just sports but everything else. Let's look at example 2 now. Weekend birthdays. So I'll read this out loud. Over the years, the percentage of births that are planned cesarean sections has been rising. Okay, so they call it C-section for short. Usually that's because of not me personally, but my wife. We've had 2 kids. We never had to do a C-section, but it's basically a surgical procedure where if it's too dangerous to deliver the baby through traditional ways, then they do a surgical procedure just for the safety of the mother and the child, of course. So anyway, some people actually have a plan too because they just know it's just not going to be safe to do a normal delivery. Anyway, probably more information you need to know, but let's keep going. Because doctors can schedule these deliveries, there might be more children born during the week and fewer born on the weekend. And of course, when someone's water breaks and then they have to, it could happen at any time. Like with my son, it happened unexpectedly on a Sunday night, 1 a.m. That was kind of a rude awakening. 2 weeks before his due date. Our daughter, we actually planned a little bit for that one, but Yeah, but you can imagine that you're going to have surgery. It's usually when the doctor's in the hospital, right? So you see more during the week than weekend. During the weekend, it'd be more just by chance. Oh, I'm ready to have this baby, right? To investigate, Mrs. McDonald and her class selected a simple random sample, 73 people born since 1993. Of these people, 24 were born on Friday, Saturday, or Sunday. Determined these data provide convincing evidence that fewer than 43% of people, so that'd be 3/7, I guess, that's kind of roughly that number. To determine these data provide convincing evidence that fewer than 43% of people born since 93 were born on Friday, Saturday, or Sunday. 100 simulated number of samples were selected. Each dot in the graph shows the number of people that were born on Friday, Saturday, or Sunday. In a simple random simulated simple random sample, 73 people, so each person had a 4-3 chance of being born one of these 3 days. Okay, so let me backtrack a little bit because there's a lot of information here. Why are we doing 3/7? Because there's 7 days in a week, right? Friday, Saturday, Sunday. So you have a 3/7 chance of being born on a weekend. Whereas you have a 4/7 chance of being born on Monday through Thursday. So that's why we chose 3/7. And we want to see if there's convincing enough evidence that fewer than 43% were born on a weekend. So you ran 100 simulations. And again, you're interviewing 73 people, but you're running these, the simulation 100 times, and you're seeing how many of those 73 people were born on a weekend. So for example, in one of your simulations, so these represent different simulations. One of your simulations, 40 people were born over a weekend. And again, you're picking 73 people from some population. So you pick 73 people and then you just ask them that question. But then the next simulation could be a different 73 people. So maybe you ask a bunch of people like in Redwood City, for example. But there's 2 people, or sorry, there were 2 simulations where of the 73 people in each group, only 22 people were born on a weekend. So we see that most of our data falls over here. Well, 30 out of 73, if I use a calculator for that, or I'll use my cell phone. Is about 41%. That's what most of my data lie. And also, what else are we going over here? Yeah, and also if we look at of these people, 24 born Friday, Saturday, or Sunday. So we had 3 people in that grouping right there. So based on data from the study, there was also is there convincing evidence that fewer than 40% of people born since 93 were born Friday, Saturday, or Sunday. So I would say there is a 6% chance that 24 people or less, because we do see, well, let me get there in a sec. We're born on Friday, Saturday, or Sunday. And actually, if I do, let me expand this one sec. So if I look at this right here, let me erase this stuff. So born since 1993. So we see there's 6 simulations here. we ran this 100 times. And this is from what you selected from your grouping. And this is gonna be a little tricky because we haven't really quite talked about this. So we'll probably have to revisit this, I think, next week and for sure in the second semester. But based on a significance level of 5%, this could have occurred by chance variation. Thus, the results are not statistically okay. So this is going to be kind of weird, and there's actually some things I haven't quite taught you guys yet. Give me 1 second. Let me just select this and expand this. So we have to revisit this definitely next week sometime, but you haven't learned about significance levels yet. So we'll have that discussion at a later time. But usually we create something called a significance level of 5%. And when you're investigating something, if you ever fall below that, then you actually say that your results are statistically significant. Otherwise, you say they're not. I know it's kind of weird. I have to have a discussion about that at a later time. But if we look at this box down below, results of study are too unusual to be explained by chance variation alone. That's when you have statistical significance. So it's not by chance that something happened, but there's actually it's actually kind of meaningful. Like for example, when you look at like COVID-19 vaccines are coming out soon, and they say how like the percentage of how effective they are. You want to see like were there other things that could have resulted in why something happened the way it did, but so you create these things called significance levels. So let me put this down here. So we need to establish a threshold or significance level if something occurred, but the chances of it occurring were less than 1%, 5%, 10%, 20%. When would it draw suspicion? So those are the things that we're going to be exploring at a later time, looking at significance levels. And I think I need to have actually more theoretical discussion about it. So we'll just go ahead and move on and just wrap things up pretty shortly. So let's take a quick peek at examples on the next page. And then we can stop there after that. So this is about rude surgeons. Is a friendly surgeon a better surgeon? It studied more than 32,000 surgical patients from 7 different medical centers. Researchers classified surgeons by a number of unsolicited complaints that have been recorded about their behavior. Researchers found that surgical complications were significantly more common in patients whose surgeons had received the most complaints, compared with patients whose surgeons had received the fewest complaints. What conclusion can we draw from the study? Explain your reasoning. So the thing is that the surgeons are not randomly assigned to be friendly or unfriendly. So we can't draw any conclusions. So essentially what you'd want to say is there's no random assignment of friendly and unfriendly surgeons. So, we just, don't know what that really means. Study did not involve a random sample of patients. So we can only apply it to the 32,000 patients from the 7 different medical centers. So yeah, so you said you have to look at the whole population at this point. Like you can't really, because you didn't create a sample that would have any randomness to it. So that'd be a problem. Now, here's where we do some random selection for the next one. A study of strength of trained memory randomly assigned. So you see the word random. 46 young adults to 2 groups. After both groups were shown 90 pictures, one group had to bend and extend one leg against heavy resistance 60 times. The other group stayed relaxed while researchers used a same exercise machine to bend and extend the legs with no resistance. 2 years later, each subject was shown 180 pictures, the original 80 pictures plus 90 new pictures, and asked to identify which was shown 2 days earlier. The resistance group was significantly more successful in identifying these pictures than the relaxed group. So it means that if you use some exercise, that might be better for your memory. That's what we're trying to, I guess, prove here. So what conclusions can we draw from the study? Explain your reasoning. So what you'd want to say for this one is that random assignment was used for the treatments here. We can draw conclusions that the difference between resistance and no resistance caused the difference in success rate of identifying pictures. The 46 adults, actually, I think I'll just stop right there. Oh. Okay. That perhaps concludes those notes. And I do need to have a discussion about significance levels. I think that might have been a little confusing, and I apologize for not thinking ahead about that. But the bottom line is this, is that when individuals are randomly selected, we can draw conclusions about the population. And we're individuals randomly assigned to groups. If the answer is yes, then we can draw conclusions about cause and effect. So, but if you say no to any of those, then you can't really, if you don't randomly selected, you can only draw conclusions about the people you selected, and you can't do draw conclusions about cause and effect if they're not randomly assigned to those groups. So it's all about just randomizing stuff when you're doing these analyses. Okay, we'll go and stop there. It's 1:38. So we'll end a little early for today. So again, just enjoy the weekend. Good luck with the other assessments. We'll meet again Tuesday. We'll make Tuesday a catch-up day, so I'll do a kind of a heavy audit. That'll be a good opportunity. Then on Thursday, I'll try to think of some kind of fun activity we could do that kind of ties everything all together. And yeah, I think that's it. I think we're all set.
Thank you.